Hello and welcome to the second installment of ITG Electronics white paper presentation series. This presentation we're going to be covering the introduction to electromagnetic interference and filtering. So a quick rundown of the contents of this presentation. We're going to start with sources of EMI or electromagnetic interference, and then best practices of circuit construction. Following that, we're going to be looking at filtering, including both the parameters in filtering and the components that make up a typical filter. Then we'll be looking at some design calculations, and finally some real-life examples. So to understand the sources of EMI, we're first going to take a look at what EMI is. So electromagnetic interference, you can kind of break down those three words to get a basic understanding of it, but it's any electrical or magnetic field or signal that is interfering with another circuit or application or product. And that can happen through two different sources. The first is radiated emissions, so that does not need a medium to travel through. It doesn't need a physical connection or conductor to transmit that noise or interference. The second being conducted, which is obviously the supplement to that. Anything that connects the source of the noise and the target or victim of the noise. Anything that is a conductive path that conducts that noise or emission or interference would be referred to as conducted emissions. And the source of EMI is typically through switching in some external source or a foreign signal that's being created. So anytime you have switching in a device, even in very advanced switching devices, you'll have some EMF being changed by that switch. You'll get spikes in current at the moment of switching, whether it's switching on or switching off, and you'll get both what's called overshoot and undershoot to match the desired signal, on signal and off signal. So basically the general takeaway from that is that this overshoot or undershoot, the outline of the actual current or signal paired up against the outline of the desired current or signal, you won't get a perfect overlap. And anything that doesn't match that signal is going to create noise in some way. And so that noise can affect obviously the equipment that it's a part of, but also it can affect the equipment around it, and even very far away in the case of radiated emissions, or even conducted emissions connected to the same circuits within, say, a house or a building. So drilling down into more of the specifics, as I had mentioned, you have radiated noise and radiated emissions. That's going to be caused by any change in an electromagnetic field or EMF. It can affect nearby devices without any physical connection, as I had mentioned. And then conducted emissions are caused largely by current spikes. So in addition to the transmission classifications of noise, there's two different modal styles of noise as well. One being common mode noise, which means you have the same noise signal on a power line or neutral and on ground. And then a differential mode noise is between a power line or neutral and the other line. So between that line and neutral or neutral and that line, it doesn't really matter which direction it's going in to be classified as differential mode noise as long as it's different on those two lines. So the next focus of this presentation, we're going to be looking at the filtering design parameters. So these are kind of the checklist for a design engineer or an applications engineer to go down and make sure they have all of this information before you can really dig into designing a filter. So the first step is to know how much attenuation of a signal is needed. So that basically means how much you have to drop or interfere with the signal before it will meet working parameters for the rest of the circuit. Because it's very difficult and very costly, if not impossible, to completely eliminate any given signal. So you just want to attenuate it down below working levels for the rest of your circuit. The frequency range, which you're targeting to get this attenuation specified in the first parameter. So that's going to be your low end, ideally. That's going to be above your operating frequency of any of the devices within your circuit. And then your high range on the attenuation frequency as well is important to specify. Are you trying to comply with a certain standard? If so, the high range will be specified within that standard. Are you concerned about like radio frequency type interference, or is your equipment less sensitive than that, etc.? These are all things that are going to be application specific. The voltage rating is important to make sure that all the components within your filter can handle whatever voltage your circuit is being powered by, because anything coming in through the power line, you're going to want to run through this EMI filter. That's how you're going to clean the power, how you're going to get a pure signal to come through without any of this interference. So the fact that all that power has to run through there, you have to make sure that the components inside the filter are up to spec for the voltage of the circuit as well. As I had mentioned earlier, the circuit operating frequency, that's going to play into the attenuation frequency somewhat. But being aware of that circuit operating frequency, even if it isn't close to the bottom range of your attenuation frequency, allows you to plan for what are called harmonics in the noise. So say your operating frequency is pretty standard at 60 hertz. So we'll start at maybe 100 kilohertz. That's nowhere close to 60 hertz, but you can have harmonics, which are multiples of that 60 represented later because of the way sound works, and it's kind of compounding on itself. You might get maybe 180,000 hertz, you'll have a big spike, and you're not exactly sure what that is. It's not coming from anything else. It's probably a harmonic of that 60 hertz operating frequency. So there's some various things you can do about that, but being aware of the operating frequency of all the different subsystems within your circuit are very important for tackling noise. The next parameter is going to be the current rating, similar to the voltage rating. You just want to make sure all the components within your filter are able to withstand, operate normally within the current specifications of the circuit. Leakage current is the basically current that goes through your filter and then travels through any of the components connected to ground. So we'll talk about some of those later. But there is going to be a certain amount of current that goes through the ground, and that's going to be potentially impactful of the ground within your circuit or the other components or systems around your circuit. So usually there's leakage specifications within all kinds of standards. So if you're trying to adhere to a standard, it may already be in there for you. Else you'll have to figure out what the maximum leakage current you're willing to allow is. And then finally, the physical dimensions are obviously going to be important in designing a filter. If you have a lot of space, you may want to utilize more of that space to get increased filter performance, maybe add another stage onto the filter, add some more components into the filter. But more often the case is you have very small space and you have to work with what you have. So being aware of how many stages or what kind of components you can fit into a given space are going to be obviously very important in designing it. So now jumping from the parameters to the components, any passive EMI filter is basically made up of two components that actually do the filtering. So those are the two components we're going to be focusing on in this presentation. One being capacitors, the other being inductors, as you can see here. To give you some background of the notation of these formulas, X denotes impedance, which is a combination of resistance and reactance. And you can think of impedance basically as how effective something is at getting in the way of a signal, or attenuating a signal, or reducing a signal. So the other symbols that you may not know here are F, frequency, and C, that's going to be the value of the capacitor in farads. And what you can take away from this formula is that the XC, the impedance of the capacitor, it increases as frequency, which is on the other side of the equation in the bottom of a fraction. So increases as frequency decreases. So the lower the frequency, the higher the impedance of the capacitor. And then in opposite fashion, the inductor increases proportionally to frequency. So you can see XL, the impedance of the inductor, equals 2 pi F, which is frequency, L, which is the value of the inductor in henries. So with the combination of these two, whether they're in series or one in series, one in parallel, various combinations can get you these different classes of filters. So as you can see here, there's high pass, low pass, band pass, and band stop. Also called a low high pass, but typically band stop is the term used. So what these little charts are displaying is sort of like the signal area being passed over here on the right. So there's no or very little attenuation over here, and very high attenuation over here on the left. So you can think about the attenuation or the impedance kind of as opposite of what this chart is showing, because it's basically showing where the signal would be passed. So if you think about the capacitor formula that we looked at in the last slide, the higher the frequency, the lower the impedance. So down here in low frequency, we have very high impedance. This is flatlined. It's basically being reduced to nothing, no signal. Very good filter. Then up here in the high frequency, it's basically the opposite. It's being reduced to zero attenuation. It's all the way up here at the maximum signal. So this would be very poor if this area is what we were trying to filter out. And then likewise with the low pass, you can think about that as an inductor. It increases its impedance with frequency. So down here on the low end, very low impedance, we see that the signal is basically max signal strength. And then as we kind of crawl onto this higher frequency, we get a much better impedance and we nullify the signal. And then the combination of these two would be this band pass. That would be if you have a high pass with the corner frequency right here being lower than your low pass corner frequency. Then you can kind of imagine if you just pushed those together from either end, you would get a band pass. And then kind of in opposite fashion, if your low pass corner frequency, so that's kind of where it starts making this bend from no attenuation to full attenuation. If your low pass corner frequency is lower than your high pass corner frequency, then you'll get a band stop. So those are kind of the four classifications of filters, and they're going to be sort of combined in some way in whatever filter you're using. Typically, you'll see a low pass filter contending with EMI because most EMI noise is up in the higher frequency range. So as I had mentioned before, there's a couple of different uses for both capacitors and inductors in filters. There's three basic capacitor types in an EMI filter. The X and Y are both rated safety capacitors, so there's standards and regulations that kind of describe what kind of capacitor, what kind of voltage rating, etc. So the X capacitors go between lines within a filter, so the power line and the neutral, or between phases if it's a multi-phase source. And so those help to fight differential mode noise between the lines there because they offer that attenuation. And then the Y-rated capacitors are between any of the lines and ground. Those will help to fight common mode noise. One of the specific points on the Y capacitors is that they are constrained by the leakage current specification we mentioned in the design parameter slide. Then kind of a special type of capacitor is called a feed-through capacitor. It surrounds a connection through an internal wall of an EMI filter. So a lot of times in multi-stage filters, you'll have part of the filter box just kind of create a wall or a barrier to prevent radiation between the different stages of the filters. And a feed-through capacitor allows you to send signal or power or whatever you're filtering through that wall. A common mode choke, this is a type of inductor. It's a very special type of inductor actually because of the way it's designed. You can kind of ignore saturation current or the possibility of saturating the core, which is this little green material here. It's a magnetic core that you wrap the windings around because these windings are in opposite directions and they, from design, balance each other out in a current standpoint, and the core actually sees no current passing through it. So as a result, you can get very high permeability cores that are normally very sensitive and susceptible to current because it's basically seeing no current. And those, obviously, by the name, you can probably guess, help to eliminate common mode noise. It's a common mode choke. And similarly named, the differential mode choke helps to eliminate differential mode noise. So these would go in line or in series with the power of the system. Whereas the common mode choke also in line, but they the core kind of traverses between lines because you'll have multiple lines, all of the lines on the same core. So it's kind of an interesting design, interesting component. So some design theory for every filtering component. So not every component that's in there, but for every component that's filtering the type of noise that you're looking for. As I mentioned, different components from the last slide filter different types of noises, common mode noise, differential mode noise. But anyway, for every filtering component on the type of noise you're looking at, you can expect about 6 dB or decibels of attenuation per octave. And an octave is a term used for when the frequency is doubled. So if you go from 100,000 to 200,000 the frequency, you can expect about 6 decibels of attenuation per filtering component of that type of noise, which balances out to about 20 decibels or dB of attenuation per decade, which is when the frequency is multiplied by 10. Likewise, if you're trying to increase your attenuation, doubling the value of the component, so if it's a 1 microhenry inductor, doubling that up to 2 microhenries can also add about 6 dB of attenuation. Or likewise, if you have it, you'll lose about 6 dBs of attenuation, which is also something to consider with components like a differential mode choke that are susceptible to current. saturation, so they'll lose inductance as the current goes up. If you're expecting, let's say, a 500 millihenry inductor to perform a certain way, but really the attenuation you're getting is maybe 6 dBs less than that, you can expect that roughly half of the inductor's inductance is being lost to that current saturation of the core. And maybe it's only reading at about 250 millihenries when the system is actually running at full current. So situations like these are useful to have these kind of rules of thumb with design theory. So this is an example of just a simulated, very simple curve. At the top, you can see we've got our voltage source. We have our voltage source resistance, which is something we would have in there to kind of just like balance, give us a better accurate reading for simulation, because every voltage source is going to have some internal resistance. And then we can see the 1 millihenry inductor here. And then in parallel, we have a 1 microfarad capacitor. And then we have our load resistance, which is also where these probes would be measuring on either side of the load. So we can see as the frequency doubles, so this is 1 octave here from 20 kilohertz to 40 kilohertz, we can see that we get 12 dB of attenuation. And if you think about 6 dB per component filtering, we've got 6 here in the inductor, 6 here in the capacitor, equals 12. So we're right on target. And then if we look at this same example, it's the exact same circuit up top. We go from 20 kilohertz to 200 kilohertz, so now we're looking at a decade, and we get 40 dB of attenuation. Again, 20 per component, we're right on target. And then comparing this to kind of show you the difference in the circuit here, the only thing changed, we doubled the value of this inductor up here from 1 millihenry to 2. I've got on the left the old circuit, on the right here is the new circuit. And you can see it previously started at 20 kilohertz at 18 dB. We've added 6 more dB from doubling that one component. So still at 20 kilohertz, and now instead of 18 dB, we're at 24 dB. So again, right on target. So here's a real-life reading from a Mil Standard 461 test. This is the CE 102 conducted emissions test. And basically in the background, you can kind of see a red line. So that's the maximum noise that's allowable by this test. So all this blue, all the signal has to be below that red line in order for it to pass. So that's just some background on the test. On the left here, you can see this is the dB in dB in microvolts of the amplitude of the noise. So we've got that scaling on the left here, and then the frequency range on the bottom in hertz, but it's in a log scale. So this was the original proposed filter for this original noise profile. And we've got, it's 3-phase, obviously. You can see we've got the 3 lines here. So we've got up front, this is all one common mode choke. This would be on one core with 3 separate windings at 500 microhenry. Then immediately following it, we've got 3 X capacitors. These are going between the lines, X capacitors, at 10 microfarads each. And then a second common mode choke. Again, all 3 of the lines on the same core, 500 microhenry. These are safety discharge resistors. So these just help the capacitors discharge any additional power they have after a filter is being shut off, so that they're safe to handle very quickly after. So these don't actually do any filtering, but they are useful to put in place to allow the filter to be handled more safely. But the next filtering component is obviously another stage of these X capacitors right here, 10 microfarads each. So you can see this is a 2-stage filter, 1 stage here, 1 stage here, and then we've got these Y capacitors to ground. These are 0.01 microfarads or 10 nanofarads. And again, the reason these are so much lower is because we've got leakage current considerations. But these help out with the filtering a little bit, so they're still in there. And then after this is a very zoomed in section of the resulting noise profile. Everything outside of this zoom is within the specs limit. It's below the red line, but we still have some areas right in here that are concerning. Even up here, as it's below the line, it's very close. So we typically want to have at least 5 dB kind of safety net below the line to make sure that everything is going to be well in compliance. But everything above the line is obviously a problem. And so in looking at this, we decided to increase some of the values of the components since we had some on hand, knowing that this could be a possibility. Well, yeah, sorry, I already gave it away a little bit. But some of the other options would be adding another stage of filtering, which would bring this down significantly, but would increase the physical space of the filter. So some of those parameters of design we talked about earlier. You could double the X capacitor. You could increase the windings on the common mode choke to increase the value of it. And that's what we ended up doing. Because the X capacitor is going to have kind of a set profile, and we can increase the capacitance there. And then by making the leads longer on our common mode chokes than we need, that gives us the ability to add some more windings, which increases the inductance a little bit on site. So if you're going into a situation where you may have to be doing some testing, you may have to increase your filtering. It's always a good idea to leave some longer leads on those common mode chokes to potentially increase the inductance. Obviously, you don't want to have extra long leads on a final product, but if you're doing some testing or something like that, it's a good idea to keep that option available so that your solution can come quickly while you're in the lab, because lab time is expensive. But as you can see, that dropped this section right here in the middle is what was zoomed in. That dropped that well below the line now. We have a comfortable, easily 5 dB margin there, and everything is very, very much in compliance, and this would be a happy result for anyone in this situation. This is the contact information for our ITG global support team. If you have any questions or you have any interest in filtering or testing or any follow-up from this presentation, feel free to contact us through any of the methods seen here. That's all I have for you on this video. Thank you for watching.